Hi there. I was just catching up with some correspondence. Welcome to the wonderful world of amateur radio and electronics, brought to you by Alpha Delta Communications. We're going to start with a summary of electronics, because to understand your current or potential hobby and amateur radio gear, you need to begin at the beginning. You'll discover that the electronic devices we'll talk about are all present as hard-working, faithful circuits in a typical transceiver. In this video, we'll look at the nature of electricity and the communications industry, which has revolutionized the way we live. We'll talk about terms like discrete, amplifier, voltage, and wavelength, and we'll go for a wild ride through an integrated circuit. Now, don't be concerned that you're not an engineer. This program is created especially for non-technical people who are interested in amateur radio. If you're baffled when you try to reset your digital watch, you'll be right at home. First, let's talk about the speed of things in the world around us. Trucks move the food we eat and most of the goods we buy at about 60 miles per hour. Jet aircraft move people to destinations throughout the world at speeds in the 600 mile per hour range. Electrons, which are the building blocks of radio, move at nearly the speed of light, 186,000 miles per second. Electrons are more versatile, faster, do more work, and use less energy than any of our other speedy examples. To understand electrons and how they work for us, we first have to back up and look at electricity and the words we use to describe it. Electrons are a basic part of the atoms which make up everything in the world. The outer electrons in some atoms, such as copper, are easily dislodged, becoming free. When electricity is generated, some of these free electrons are released to either strike and dislodge other free electrons in nearby atoms, or perhaps just zip on past. In this way, free electrons are passed down along the line of atoms. Basically, when electrons move in a stream, they typically do one of two things. They convey information or intelligence such as voice, data, or video, or they provide a flow of energy to power lights, motors, or decision-making circuits in computers, communications equipment, or other similar devices. Electrons, as it happens, flow in a current, much like water. The pressure of this flow of free electrons is measured using the term volts. The amount of electrons, like the volume of water, is measured in amperes or amps. For example, a very large, slow-moving river would have a very low voltage, but a very high amperage. Not much pressure, but lots of volume. On the other hand, a small waterfall down a cliff would have a high voltage or pressure, but low amperage or volume. As a comparison, a small welding machine operates at a voltage as low as 15 volts, pretty low in pressure, and as high as 1200 amps, very high in volume. Electrons have what is called a negative electrical charge. It's a term from physics which we won't go into here. Electrons are made to move when they're influenced by an opposite or positive electrical charge, and they move in a direction toward this positive charge. A car battery, which provides the power for your auto electronics and mobile radio equipment, has positive and negative terminals. The electrons flow with a certain level of pressure, volts, and volume, amps, from the battery's negative terminal to the positive terminal. The engine control module, radio, headlights, and other electrical systems require a certain amount of work, watts, to operate properly. All of this is kicked into action when you turn on the ignition key, which completes the battery circuit. Both electrical pressure and water pressure are used to do work. When you multiply volts times amps, you get a measure of the work being done by the current flow, watts. Now there is a natural resistance to the flow of either water or electricity. The diameter of this hose offers resistance. The smaller the hose, the greater the resistance. Resistance to the flow of electrical current is measured in ohms. Resistance to the flow of electrical current is what makes light bulbs glow and stove burners get hot. This is something we want. Simple resistance is also what causes us heat problems and potential failures in our electronic equipment. In this case, something we definitely don't want. But what does this mean to us? All the devices and communications equipment simply change, control, or limit the flow of electrons. How they do this is what gets complicated. For one thing, manufacturers have a choice of materials to use in the design of semiconductor products. Some materials are either good or poor conductors of current. They offer little or a lot of resistance to electron flow. For example, copper, gold, or silver are excellent conductors. They have plenty of free electrons, so they're often used to allow current to flow freely. Whereas rubber, glass, ceramic, or even some gases have few free electrons. They are recognized as insulators or poor conductors and prevent or slow the passage of current. In between, we have materials which are neither good nor poor conductors. They're in between conductors and insulators. They're called semiconductors, like silicon and germanium. We'll talk a lot more about these later. One other point I need to cover: the differences between alternating current and direct current, AC and DC. We start out with alternating current for most uses today. AC is used primarily because there's less loss of power when it's transmitted over long distances. AC can be transmitted practically up to 600 miles from the generating source. DC suffers huge losses when transmitted much over a mile. Each time a user takes power away from the line, a transformer transforms it down in voltage for normal usage. Most households have 220 volt AC brought in from the street to run things. Alternating current is doing just that, alternating back and forth between positive and negative at a rate of 60 cycles per second, or hertz in the United States. As an example, most household appliances operate on AC. Direct current is a steady flow in just one direction and is represented by only half the AC wave when seen on an oscilloscope. Notice the apparent ripples. We'll talk about these later. DC applications include flashlights and auto-ignition systems with the power supplied by batteries of various voltages. Many of our radio systems use alternating current and plug directly into a wall socket. All of the transistors and integrated circuits contained in these systems need direct current. So the AC is converted to DC by devices called rectifiers in the power supply circuit. They allow current to flow in only one direction. Voltages, whether they're AC or DC, can range from a millionth of a volt to several million. For example, the weak FM radio signal that your portable radio pulls in can be measured at a few millionths of a volt. A flashlight bulb uses either 1.5 or 3 volts, while a computer chip calls for just 5 volts. A battery-operated transistor radio operates on a 9-volt battery, and a car battery puts out 12 volts. A light bulb in your kitchen and the coffee maker use 110 volts, while the electric clothes dryer and the kitchen stove use 220 volts. Moving to the higher voltages, the big power tube pushing a signal up a radio tower operates at around 10,000 volts, and a stroke of lightning during a summer storm can hit the ground carrying 160,000 amps shoved along by 100 million volts. That's a good start on electronic theory. Now let's turn our attention to some of the hardware buried deep inside amateur radio equipment. Vacuum tubes were the foundation of electronics from the 1920s through the 1950s. Tubes could amplify signals, control current, and turn on and off like switches. Then, Along came the solid-state transistor to change all that. Solid state simply means a device whose operation depends on current moving through a solid material, like silicon, as opposed to movement through a vacuum, as in a tube. Transistors can do all the things a tube can do, plus, and these are major advantages. They are much smaller, more reliable, use far less power, require no warm-up time, and are very, very fast. One of the first semiconductor devices was the diode, or rectifier. These function as one-way valves, allowing current to pass in only one direction. That's how they convert alternating current to direct current. Remember, DC flows in one direction only? Other devices downstream from the diode rely on this one-way current flow for their continued health and operation. Some semiconductor devices like transistors can also be made to amplify as well as control. That is, they take a very weak signal and convert it to a much stronger one. Sometimes 1,000 times stronger. When an electronic component is designed to do only one thing in a circuit and has just one circuit element implemented in the device, we call it a discrete device. These are typically transistors and diodes. However, if it's capable of more than one circuit function and has a number of circuit elements like this much more complex component, it's called an integrated circuit, or IC. This means that it has many transistors and diodes integrated into a single, unified structure. I made a tour a few days ago which we taped. I think now might be a perfect time to show it to you. This circuit board for a simple AM/FM portable radio is sort of the payoff of many of the things we've talked about up till this point. Let's see what's here and what each piece does. We'll start over here. This is a transformer, much like the one on the pole outside your house, but on a much smaller scale. It takes the 120-volt 60-cycle AC current from the wall and transforms it down to a more usable voltage required by this particular circuit. This reduced AC goes to these rectifying diodes, which are part of the power supply. The diodes change the lowered AC to DC, which is required by the different semiconductor devices downstream. This DC voltage is now passed to this filter capacitor. You recall those bumps or ripples in the DC flow? Well, the capacitor smooths out those ripples, creating a pure form of DC. Without pure DC, this radio circuit would produce a low-level hum, which, after all, you would find annoying. We also need this pure form of DC for the proper operation of the semiconductor devices. The voltage of this direct current is still too high, so it's passed through resistors. Remember resistance? It impedes the flow of current. Okay, we put that resistance to work. This resistor reduces the voltage level down to 5 volts for this integrated circuit chip right here. The flow of this DC is in the milliamp range, very low in volume. This other resistor here puts out 12 volts, still in the milliamp range in this particular circuit for this transistor here, which is the first amplifier for the radio signal coming in. That lead on the left brings in that faint little signal from the antenna. The middle lead here provides the control voltage to operate the amplifier, while this third lead sends the amplified louder signal out. The listener has no control over this first amplifier. He runs full on all the time to recover the weakest radio signal possible. You've probably heard this transistor referred to as a small signal device, since it operates in the milliamp range. 1 ampere of flow is sort of a fence between the small signal and power devices. In this radio, there are other stages between the first amplifier and the speakers, which tune and convert the radio signals to audio signals. One of these is an audio amplifier transistor. When you turn the volume control higher, what actually happens is that the signal voltage here at this amplifier is raised very slightly. A very small change here produces a big change in the signal going to these audio amplifiers. They boost the signal again from the amplifier connected to the volume control and pass it to the speakers. They're called power transistors since they operate at approximately 5 amps. Each one of these produces about 25 watts of power at its respective speaker. Just a couple of other points. One of the leads from this transformer bypasses the rectifier diodes. This lead supplies AC power to turn on the little light on the radio dial. Interesting tour? If that electronics board I was strolling around were on an amateur radio transceiver, the circuitry would have other complex functions, such as oscillators and other circuits to generate radio frequencies. And speaking of radio frequencies, let's talk about them. You'll recall that we compared electricity to water in terms of pressure, volume, and resistance, volts, amps, and ohms. The comparison is valid for radio, too. Radio waves act very much like ripples on the surface of a lake or pond, especially when they radiate from one source, like a radio transmitter. Drop a rock into a still pond, and the waves move outward until they either hit something or run out of energy. In electronics, these waves are generated by that oscillator we just mentioned. Notice the similarity between these waves and the electrical trace? So, we need to learn 3 more terms you'll deal with all your lives as amateur radio operators. The first term, wavelength, is the distance between the crests or tops of the waves. The next term is frequency, which is the number of wave crests which pass a given point in 1 second. The final term, amplitude, is measured from the bottom of the wave trough to the top of the crest. Actually, the amplitude is expressed as half the total distance. As a matter of fact, the greater the amplitude, the stronger the wave is, both in water and radio. Radio waves themselves are a small section of a much greater array called the electromagnetic spectrum, which ranges from radio and TV through visible light to X-rays and gamma rays. Here's a general layout. When you look at it, the energy in this spectrum controls our lives. We identify areas of the spectrum in terms of hertz, or kilohertz, or megahertz, which are measurements of frequency. For example, AM radio is way down here in the 540 to 1700 kilohertz range. We call this the AM broadcast band. The FM radio band is from 88 to 108 megahertz. A band is actually a range of frequencies. These bands are allocated by our government and by international agreements. Now we need to get a closer look at the spectrum and the bands where you'll be operating as amateur radio users. This segment ranges from AM radio up to the area of microwaves and radar. You'll hear these radio bands referred to in one of 2 ways, by frequency or by wavelength. And here's a point of possible confusion. The higher the frequency, the shorter the wavelength. Just keep that in mind. Here's how it works in day-to-day usage. There's an assigned amateur band here around 7 megahertz, but we refer to it as the 40-meter band. The wavelength of a radio signal at around 7 megahertz is 40 meters. This is a very popular area for shortwave or high-frequency radio. Another example is the 10-meter band, which uses frequencies in the 28 and 29 megahertz range. There are 9 high-frequency bands assigned for amateur radio, and several more in the VHF and UHF range. Each one of these bands has different characteristics in miles of range, seasonal usability, and sensitivity to sunspots. You'll find that sunspot activity can have a profound effect on which amateur radio band you choose to use. Okay? Now let's see how you get a signal out on that band. When you talk into a microphone, it creates an audio signal, which has both frequency and amplitude. It looks like this on an oscilloscope. Down inside your transmitter is an oscillator, which is generating a carrier or continuous wave. This wave has a certain wavelength, depending on the band you've selected for a particular purpose. A carrier wave looks like this. By the way, this is what you hear when you listen to code, rapid interruptions of a continuous wave. When we combine the audio signal and the carrier wave, we create a high-frequency modulated signal, which looks like this to us. Amplifiers downstream from the modulator boost the power of this signal in wattage, and out it goes up your antenna lead and out into the air. You really can see a radio wave. It just takes an oscilloscope to do it. As long as we're looking at radio waves, let's look at two more, AM and FM signals. In AM, which means amplitude modulation, the audio signal changes the amplitude of the carrier wave. On the other hand, with FM, which stands for frequency modulation, the audio signal modifies the frequency of the carrier wave. Thunderstorms create atmospheric amplitude variations which cause static on AM. FM is static-free since it does not detect amplitude variations. FM can produce a richer sound because the FM band uses a much broader frequency width for each station, allowing for much better audio reproduction. We might as well show you one other signal. Since so many of you will be using it, we'll look at single sideband. Instead of looking at the signal from the side, we need to look at it from the end. You're now looking down the line at a signal on the, let's say, 10-meter band. You're on a frequency of 29 megahertz. What isn't apparent is that your signal is creating two sidebands, the lower one at 28.998 and the upper one at 29.002 megahertz. You simply use one or the other sidebands, putting all your power into a much more efficient signal. More distance for the same juice. That's single sideband. We've covered a wide range of topics here, from basic electronics through the waveform of a high-frequency radio signal. It will all begin to make more sense to you as you move forward through your studies for your amateur radio operator's license. The book, Basic Technology for the Amateur Radio Enthusiasts, which came with this video, will help you immeasurably. You'll be joining a truly worldwide hobby which has not only a fun side, like talking to other ham radio fans in other states and other countries, but has a serious public service side too. Amateur radio operators have played vital roles in disasters of all kinds, often providing the only reliable communications possible. They also provide public services such as messaging, medical assistance calls, and staff communications at sporting events. From Alpha Delta Communications, here's a hearty welcome to the airwaves. I'll listen for you on the air.